All right. So we left off last class. Looking at how we do back a little bit, how we find the probability of being above or below certain values. So just kind of recap a little bit, and I think I said, I had an extra example in here that we didn't go through in class, but I can kind of go through it right now, just to give us a recap of where we're at. And then I also showed you how to do this in Excel, right? So we kind of worked through that last class. So we're going to start off with these normally distributed variables. We're going to know their mean. So here I'm told the mean is what? 28.89. I've got this variance of 26.16. And I want to think about what I want to do is convert this normally distributed variable into, this is a very good marker, into a standard normally distributed variable. So there we go. So we said those are kind of our z values. And then we're interested in the probability that we see what temperature be 42.85. So 42.85 or anything greater than that. Okay. So that's kind of our setup. We've got all the things that we need to calculate a z-score. Right? So if you remember what that equation was for our z-score, we just took the x value we were interested in, subtract the mean, and divide by the standard deviation. Okay. So here, right, my cutoff value is 42.85. My mean, 28.89. Standard deviation, I have a little bit of work to do. I was just given the variance. But this is going to be what? The square root of 26.16. So something just a little bit over 5, right? Once I get that z value, right, and I believe, if I'm looking at this, I'm going to go out on a limb and guess that it's 2.73, right? But that's not the probability, right? That's just my z value. It's the number of standard deviations away. The average temperature in February of 43, or almost 43 was, how many standard deviations away from that mean was it? Just under 3, right? So it's pretty far away from that mean. We said anything that's like more than 2 standard deviations with the mean, it starts to be a pretty large z value, right? Pretty unlikely to see things that are more than 2 standard deviations away. So right away, if we're thinking about the area to the right of this, this should be pretty close to what? I just said it's pretty unlikely we see something this many standard deviations away. That means that this is a fairly low probability, right? The probability we see something that's 2.7 standard deviations above or anything even further, it's going to be relatively small. Which, kind of thinking about it differently, what's the probability that I see this z value be below 2.73? Well, it should be pretty high, right? In fact, if I go, oh, I didn't mean to minimize this, so let's go here, and then we'll go here. So if I look up 2.73, well, first of all, I can't show this all on the same screen, so we got to make sure, okay, that's the column for my second decimal, right? 0.03. So we'll go down here. That was my column, so 2.73, 0.9968. But remember, the table always gives me the area to the left. I wanted the area to the right. So I would subtract that from 1. So what? 0.0032. Or the probability that I saw February temperatures be as high as they were in 2017, or anything even higher than that. Probability of 0.003, about 0.3% chance. Okay. Any questions over anything here? Like I said, this is, we went through some examples last class. I kind of had to save this one so we can start off kind of thinking about where we left off today. So here's where, let's see if I got a different blue marker because I might need 3 colors here. So it's a little bit tricky going to the next thing that we're going to talk about. I'll get the slides up there so we have some idea. Okay. Oh, maybe there we go. So that was kind of I guess, the conventional use of those tables that usually you start out, you're told some cutoff value for X. You then want to turn that into a Z value. Once you have that Z value, you can look it up in the table and find that probability to the left of that Z value. Or use the cumulative probability. So that was like we start with an X value, we end up with a probability at the end. Right? So the inverse process is going to be sometimes what we're interested in is say, okay, what X value, right? So it's like what X value would be the cutoff for being 2 standard deviations away, right? In fact, I might not even know 2 standard deviations. Maybe I tell you what's the probability, or sorry, what cutoff value X would give me the probability of, I don't know, 0.95. So now I'm starting out in this inverse process where I know the probability and I want to find kind of this cutoff value for X. Okay? So how am I going to be, how can I do that? Well, we can use the table to work in the inverse or in reverse, where instead of looking up the Z value using the row and column headings and then finding that probability associated with that Z value, I can look up the probability in the middle and then go over and up to my row and column headings to figure out, well, what Z value is associated with that probability. Once I have that Z value, you can kind of imagine if I had this Z value, so maybe it's 2, and I had the mean and the standard deviation, well, I've got one equation, one thing I don't know, I can do a little bit of algebra. So instead of doing the algebra like that, rearrange this equation every single time, we also kind of have that. It's always going to be when I rearrange this equation, this Z-score equation to solve for X, here's going to be my inverse formula. Okay? So I don't have to plug the numbers in and do the algebra every single time. I can just remember that once I look that probability up in the table, I find its associated Z value. Well, now it's just a matter of plugging in that mean, plugging in that Z value, and plugging in that standard deviation. So mean and standard deviation are going to be given to us. We can find Z by using those tables in reverse. Then we've got everything we need to plug in to figure out what that cutoff value for X was. So hopefully something a little more sense after I put some numbers to this, right? So let's maybe put some values to this. I think it'll help kind of solidify what we're doing. So we're now going to be working in the inverse, right? So I've got the inverse formula written up there on the other side of the board. We can think about a scenario where I've got this exam. The average was a 72. The variance was a 64. What's the lowest possible score, or kind of what's the cutoff test score for being in that 90% or being in that, being in the top 10% or being better than 90% of the other test scores, right? So you kind of think about like, we're almost like finding kind of percentile cutoffs, right? It's just, we're doing it for continuous data as opposed to, I think when I showed you before, we had kind of smaller data sets and then we didn't kind of, we had to use that goofy position kind of to find the percentile. Here, we can kind of rely on what we know about the normal distribution. So start out drawing this out just to kind of visualize what we're doing is now we're basically going to be working from the bottom up compared to what we did before. Okay? So the thing that we know is that this original variable is centered with a mean of 72, has a variance of 64, which would be what? Standard deviation of 8. Okay? So if I want to know what the cutoff is, like what test score would be the cutoff such that it's better than 90% of the other test scores and kind of the cutoff for being in that top 10%, right? I'm being told essentially the probability or that area that I want in the left tail, right? So I know that this is 0.9, right? So I have to use the table to work in reverse, okay? So what Z value essentially is going to give me 0.9 in that lower left tail. So here's where it gets a little tricky because we're constrained to 2 decimals. When I show you how to do this in Excel, we'll see that we don't run into this issue. But let's say I'm looking at kind of my table. Well, first of all, if I want the area to the left of my z-value to be 0.9, I know that this z-value should be what? Greater than or less than 0? So remember, the standard normal distribution has a mean of what? We said it has a mean of 0 and a standard deviation or variance of 1. Right? So what would the area to the left of 0 be? Well, the probability I see the mean or anything below it. 0.5. Just 0.5, right? Symmetric distribution, the mean exactly splits it in half. So if I want 0.9 to be the left, well, I've got to get a value that's larger than 0 or positive. Okay. Now, so I go to my table, I'm looking at kind of the positive z-value side of it. And I'm going to look up now, instead of using the row and the column heading, because that was how I looked up a z-value. Now I have the probability. So when I go to this table, these values in the middle all represent probabilities, or kind of you can think about the area in that left tail, right? Or the area to the left of whatever z-value we're looking up. So I'm going to try to find the value that's closest to 0.9, right? That's the probability I wanted. So I'm looking through here. Looks like it's in between these two. I can't find exactly 0.9, but I can figure out which two are the closest, right? So here, I'm in between these, which have a corresponding z-value of 1.28 and 1.29. So I know the z-value that I want. It can't be real precise, but I know it's somewhere in between 1.28 and 1.29. The way that we're going to kind of approach these problems where it comes to iClickers, exams, if we're working through these on the homework, right? Just always choose the higher of the two, right? Occasionally, I think some of the algorithms on the homework, if that gives you an issue, sometimes just taking the middle value, so 1.285, kind of should help kind of any of those algorithm issues. But the way that I'll do it in class is I'll just kind of always use the higher of the two. When it comes to the exams, I'm giving you kind of the different responses. I'll always calculate them. If we're in between two z-values, just use the greater of the two. And I say greater if they were negative, use the larger negative value. So the largest in absolute value. So here we'll use 1.29, right? We're in between that z-value of 1.28 and 1.29. So we're going to use the higher of the two, 1.29. We know that the area to the left of 1.29 is approximately 0.9. Right? It's a little bit higher. Where is it? Oh, I have to go back down. I think it was 0.9015, but we're constrained to 2 decimals. That's the best we can do. Okay. So now that I have this z-value, I know that the cutoff test score for the 90th percentile has to be 1.29 standard deviations away from the mean. Well, that's all that inverse formula is saying, right? In order to calculate this x value, take the mean and add to it however many standard deviations away you need to go times whatever the standard deviation is, right? So here, right, 72 plus 1.29 times 8, right, it should give us, oh, I don't know, it's approximately 84-ish or something like that. So if we actually get this entered into our calculator, no one else gets to it before I do, right? Oops, one more. 82.3, that was close. Right? So we start out with the probability now. So it's almost like we're down here with the standard normal distribution. We use that probability or the area to the left to find our z-value, or the number of standard deviations away we need to go. Using that z-value, our mean and our standard deviation, we can then figure out what that cutoff is for the original variable x, which was test scores. Any questions or anything here? Yeah.
So for the 1.29, did you look at the Z chart with the 0.9? And then, because I'm just looking at how you pick that.
Yeah, so I wanted the area to the left to be 0.9 because I wanted the cutoff that had, I wanted this test score that was the cutoff for the top 90%, sorry, that was better than 90% of the other test scores, or kind of the cutoff for that top 10%. Right? So when I went to my table, I know the probability. The values in the middle, these are probabilities, right? So if I want to start with a probability, I have to find that 0.9 somewhere in this table. The closest we could get, right? We said we were in between these two values, right? These are as closest to 0.9 as any of the values here. The corresponding z value that would give us that desired probability or area in the left tail would be 1.28, 1.29. We said we'd use the higher of the two. Yep. So I think the next one, I think I had it set up as eye clickers, but I think we'll kind of walk through the one of them. Looks like most of you are engaged today, so this is good. So I think the next one says, what's the cutoff for the, oh, I already forgot. It's either bottom 33 or bottom 40%. I forget which one I did in the Excel example and which one I did in the slides. Bottom 40%. Okay. So you've got the same setup, but now we want the test score that's going to be the cutoff for the bottom 40%, right? Or the area to the left of this cutoff value is going to be 0.4. Now, when I drew this right here, I plotted that point on the left side of the distribution. Why did I plot that point on the left side of the distribution? It's the bottom half, and because it's the bottom 40%, what cutoff would be for the bottom 50%? Just my mean. Well, what's my mean? 72, right? We still have that standard deviation of 8, right? So then change the numbers there. So that's kind of why I knew I could plot that there. Right? I just want to make sure that, because you don't always necessarily know if it was the bottom 60%, well, then I would know it would have to be somewhere over here. Right? So I have to work in the reverse. So I've got to start out actually down here dealing with that standard normal distribution. We said it's centered around 0. So the number of standard deviations the way I need to go, I should find a negative z value here. Okay? And it will be that z value that gives me 0.4 in that lower left tail. Okay? So from here, we've got to use the table again, working in the reverse. We know the probability. Excuse me. I said we know that we're dealing with a negative z value. So here, okay, so I'm looking at these numbers. I've got to find 0.4, right? Looks like I'm in between these two values, right? This is the closest I can get to 0.4. So the z value that would give me that desired area in that left tail is negative, excuse me, 0.2, and I got to scroll up here, negative 0.25 and negative 0.26. We said we'll always use kind of the greater in absolute value. So we're going to use negative 0.26 here. So the cutoff test score for this bottom 40% is going to be what? 0.26 standard deviations below the mean. Right? So right away, I know this value should be less than 72. Right? Now, from here, it's just a matter of I've got that inverse transformation formula. I can plug everything in. I've got everything I need. So 72 minus 0.26, right? Don't ignore if you've got a z value that's negative. Make sure you're using a negative sign there. Next times negative 0.26 times 8. Yeah.
Would since it's negative, would 0.25 like on the test would like you want?
Yeah. So when I say take the higher of the two, think about it as ignoring the negative sign. So the absolute value, right? So the greater in magnitude. The larger positive value or the larger negative value. Yeah, that's why I chose that negative 0.26 there. Questions? Yeah.
How did you know it was negative 2.6? Like you knew it was going to be a negative.
So not how did I find out the table, but how I knew it was negative.
Yeah.
The reason why I knew it was negative is because what would the cutoff score be for the bottom 50%? It would be whatever the mean is. So in order to get an area that's less than 0.5, I know that I'm going to have to be looking at values that are below the mean. So there are going to be a certain number of standard deviations below the mean, which are with our z value that's negative. Yep. Because the z-value is centered at 0, right? The mean will always have the z-value of 0. Okay. Because the z-value interpretation is the number of standard deviations away from the mean. Well, the mean is always 0 away from the mean. And so then we know, okay, well, if I want an area less than 0.5, that's going to have to be values that are below the mean, which is going to correspond to negative z-values. Okay. Good point. Other questions? At this point? Yeah.
So where did that 0.26 come from?
Yeah, so we'll go through that one more time. So to be clear, what I wanted was this cutoff value that gave me, the cutoff to the bottom of 40%. So I know that the area that I want in that left tail, or that probability that I'm looking for, is 0.4. So I'll go to my table and try to find that probability of 0.4. Now the values in the middle represent probabilities. The row and column headings represented z-values, right? We don't have the z-value. We're working in reverse now. So I've got the probability, so I'll look that number up, in the middle. So I go down here. What's closest to 0.4 in between these two, right? So the z-value that corresponds to that probability of 0.4 would be negative 0.2, and then we have to go up. Negative 0.25, negative 0.26. We said we take the higher of the two, or the higher magnitude of the two. Is that? Okay.
Yeah, that's
Okay.
exactly.
Other questions on this? Okay with this? So I'll show you how you do this in Excel. I'll get the next Excel assignment up after class today. You can kind of start working on that. You only be able to do like the first third of it, but I'm just getting it up there so that you can work on that part since we're, really close to the time that we actually covered it. Next week, hopefully next week, we'll start talking about sampling distributions, and then kind of the rest of that assignment kind of has to deal with confidence intervals and sampling distributions. So, excuse me. So I've got kind of what the work we did up here. Here's kind of a summary. We talked last class about using that norm.dist function. We're now going to be able to work in the inverse by using this norm.inv. So I had saved what we did last class right here. Okay. And then I'll post this under the in-class data section. Kind of has the blank files up there, but here has all of our work. So we were working with that temperature data using that norm.dist. Here I'm going to kind of use this rain worksheet to do some inverse stuff, okay? So I'm just going to focus on 1 month just to keep this easy for us right now. So I'm just going to delete everything that's not June, not July, and we can get rid of all of this, okay? So let me see here. So you guys can actually see what I'm doing. So you can kind of think about, we're going to now have to be starting out with some desired probability. Right? So I'll show you what this kind of looks like if we were doing that test score data. So off to the side, the mean and the standard deviation we had was what, 72 and 8, right? I then thought about, okay, I need to know what area I want in the left tail, right? Or kind of the probability that I wanted, right? So when we had 0.4, right? We wanted to work in the reverse, right? We had to look up 0.4 in the table and find the corresponding z-value. So there's two ways we can do this. The first is I can use this norm.s.inv function. That tells Excel, okay, use the standard normal distribution, but instead of like before, when I use norm.dist and I told you a z-value, I'm now going to give you the probability and I want you to tell me the z-value. So notice the only thing I have to tell it is that area that I want in that left tail, or that desired probability, which I've got it up here in the cell. All right, so I'm just going to click on that. All right. Whoop. All right, so notice I can be a lot more precise using that norm.s.inv. Instead of negative 0.25 to negative 0.26, it gives me, negative 0.253347 out to whatever decimal I really want. Okay, so it doesn't have to rely on kind of rounding it to 2 decimals. I then say, okay, what is this cutoff value for X? That was I originally was interested in. What's the cutoff test score for that bottom 40%? Well, now it's just using Excel to be our calculator. We've got that inverse transformation formula. where we just take the mean, we'll add to that the number of standard deviations away we want to go, multiplied by that standard deviation. Just using Excel to be my calculator here, right? But using it to find the cutoff value using the inverse transformation as a calculator, we had to use that norm.s to I and v to figure out what that z value is.
Could you show the formula? For the
Yep.
values?
So all we should have to do there is tell it norm.s, right? So norm.s tells it use a standard normal distribution or look for a z value. And then norm.s.I and v tells it, I'm going to give you a probability. I want you to tell me the z value that corresponds to that. When we're using the norm.dist, we were telling it the z value, sorry, norm.s.dist. We were telling it the z value, and then it returned to us the probability. We're just working in the inverse now. Okay. Any questions on that before we keep moving here? So I can be a little bit more precise. I don't have to be constrained to 2 decimals when I'm using this in Excel. Okay. So what that, just to show you another example, well, yeah. So also if I set it up this way, it's kind of nice because like I can do a whole bunch of, I could do the 0.9, I could do 0.99, right? In fact, I could do 0.5. What value, if I'm telling you everything correctly, if I put 0.5 as the desired probability, what cutoff value for X should I see here? Not 50. All right, so the Z value that would correspond to having 0.5 in the tail would be 0. Right? Because if I want that desired area in the tail to be 0.5, well, I know the mean exactly splits my distribution in half. The probability of the left and the right of the mean should be 0.5. Right? So the Z value of 0 is 0.5 to the left, 0.5 to the right. But what would my cutoff value for X then have to be? Just the mean. Why? Because if I plug the Z value of 0 in here, 0 times anything is 0, and that cutoff value should just be the mean. Sure enough, it's exactly what I get. Okay. Any questions on that? I'm kind of just saying things in a slightly different way and trying to give you different ways of looking at it to kind of make these ideas sink in. I'll change this back to 0.4, right? So it matches up with the problem we did. Okay. Yeah.
I'm sorry.
You're good.
Show the cutoff value.
Yeah. So all I'm doing there is using Excel to be my calculator. And every time I want one of these things, I just click on that cell that it's in. Yep. So how could I do this with the rainfall data, right? So maybe I want to know, okay, in June, what's the cutoff value for rainfall, right? Such that, I don't know, there's a 33% chance I'll see that amount of rainfall or anything below it, right? So the desired probability I want is 0.33, right? That whatever cutoff value for rainfall that I'm looking for, it's going to be the cutoff for the bottom kind of 33%. So kind of give you a visual to go along with this as we work through Excel. Got a slightly different variable now. So I've got this rainfall variable. What's its mean? In June, it's about 4.2. Standard deviation is about 1.54. If I'm plotting this and I'm thinking, okay, I know the desired area in that left tail I want is 0.33. So if I'm plotting this relative to the mean, where should that cutoff score be? Relative to the mean, would I plot it on the right or the left side? Yeah, it's the cutoff value for the bottom 33%. Well, the mean would be for the bottom 50% or probably 0.5. So I know that I'm going to be somewhere below the mean. I know that the Z value that I look up should be negative, right? Because I'm going to be a certain number of standard deviations below the mean. Okay. So how can I use Excel to do this? Well, I could break this down to steps. So I could do norm.s.inv, tell it that desired probability that I want, right? And then just kind of use Excel to be my calculator. Here's the mean. Add to that the number of standard deviations the way I need to go, multiplied by that standard deviation. Okay. And I'll label these here just so it's a little bit clearer. So variance, standard deviation, right? So I basically just did the exact same thing I did over here. It's just I'm using a different cell kind of for that desired probability. And obviously I have to use the mean and the standard deviation of June temperature, or sorry, June rainfall here. Okay. Any questions on this? Keep moving. Got one more thing I'll show you here. So last week we said I can do the intermediate steps using norm.s.dist, but there was a shortcut to avoid it all, which was just use norm.dist, and it did all this work behind the scenes for me. Same kind of idea. Oops, I forgot my equal sign. I can use, instead of norm.s.inv, I can just use this norm.inv function. It'll compute the z value behind the scenes for me, put it into that inverse transformation formula, and just spit back out at me whatever that cutoff score for x is, or cutoff, in this case, rainfall for x is. Okay? So what are the three things that it's going to need? Well, it needs to know how to find this z value. So it needs the desired probability. So that's the first thing. So we've got 0.33, comma, whoops. So using that, it can find the z-score, but the other things that it needed to throw into that inverse transformation formula was the mean and the standard deviation of our variable. So the mean of our variable was up here, standard deviation down here. Now it should do all this work behind the scenes. And if what I've said is correct, it should give me the same answer I found before of that 3.52.
So we don't have to do the add and this multiply?
No, it does all that for you.
Um,
So it's doing it behind the scenes, right? So you're getting the same value because essentially what it's doing, you told it the probability, the mean, the standard deviation. Excel is looking up that probability, finding the corresponding z-score. It's then taking that z-score, taking the mean and the standard deviation you told it, plugging those into this formula, and then spitting out at you that cutoff value. So it's just doing, it's all like pre-programmed. It's doing it all behind the scenes. Now, the reason why I show you how to use that norm.s.inv and the norm.s.dist is because down the road, we're going to use those functions for other things, right? But for the sake of that first third of the Excel assignment, you can use the norm.dist and the norm.inv. You can have it do the work for the behind the scenes for if you want. Or you can break it down to steps just to, if you want to double check yourself. Okay. Any questions over anything there? You want to see a cell again or? Okay. All right. So I'm going to save this real quick. So when I post it, it'll have everything that we did today. For the rest of class, we're going to switch gears just a little bit. Right? So this is going to be a lot less technical and a lot more kind of conceptual. But I think it's interesting, and it's really, I think sometimes about skipping this section, but I think it is actually really important when we're actually looking at real data to think about some biases that could exist. So we never really get to see population data, and kind of behind the scenes, I wasn't really explicitly saying it, but in my z-score equation, I was always using the population mean and standard deviation. So it's almost like we were looking at population data. Most of the time we can't see population data, all we have is a sample. So we want to make sure our sample is as representative of the population as we can get, right? Because, if I'm interested in the average income in the US, sorry, here's a good one. Average height in the US, and my sample is only collegiate basketball players, I'm going to have a pretty big bias built into that sample, right? I'm going to see taller height on average than I would for the population. So however I'm selecting my observations, I want to make sure that it's random, right? That I'm getting a representative sample of the population. So we've got two different things. We can see either finite or infinite populations. I'm not going to spend too much time on infinite populations because we're not going to deal with that. It's usually some data generating process, right? That can kind of just continue on forever. Even if we're thinking about something like the population or the income in the US, we can put a limit on the number of people that are in the US, right? There is a finite kind of population. So that's what we're going to be dealing with, right? These finite populations. It's not feasible to generally get that population data. So we're left with a sample. We'll then use that sample to make inferences about the population. So because we're using that sample to make inferences about the population, we need to make sure it's not biased, right? So there's a couple different things that's kind of out of the way. We'll just remind ourselves. Our population is capital N, right? That's the number of observations that will be in the population data set. Lowercase n is going to be the sample size from our sample data, right? Or the number of observations in our sample data. So we're going to be dealing with lowercase n when we're dealing with samples. We can randomly sample with or without replacement. So all this means is that, like, if I was taking a sample of 5 of you guys and I put all your names in a hat, and I draw one of your names out, and I don't know, maybe I record what your grade is right now, put the name back in the hat, shuffle them around, take out another name, write that kind of person's grade down, and then, you know, maybe have a sample size of 5. If I do that with replacement when I'm putting the name back, what could be an issue, especially with a class like this small? It's not that many people, so what might happen? If I've got 5 observations, I might end up with the same person. Why is that a problem? So I think here I say that it's better to do it without replacement. Once you kind of took someone's name, you don't put it back. Well, the reason why is because when we think about the mean, I said one way you could think about it was like every single X value or every single observation was being weighted equally, right? Well, if I draw the same person twice, they're going to have the same value for X. They'd actually be getting kind of twice the weight, right? And I don't want that to be the case, right? Every single observation should only be counting or kind of having the exact same weight over whatever I'm calculating, even that's just the sample mean. Okay? So usually it's better to do without replacement, right? I'm going to skip this because, like I said, we're not going to deal with infinite populations. And we really only have one more thing to check, which is we have to make sure that our observations are independent from each other. And sometimes we have a data generating process. It inherently kind of the outcomes you see will be dependent on each other because random numbers are kind of follow a certain program in computers, but we don't have to worry about that. Okay. So we'll just deal with finite population. So we can still run into some problems, right? So let's say I want to know something about the average income in the US, but I know that there exists kind of a pay gap between the genders, right? So I know that the population as a whole is about 50-50 male female, right? We have a longer discussion about gender and things, but for the sake of this, you know, we're thinking about, we've got kind of male female, and we're thinking about if we took a sample and let's say we wanted a sample size of 100. I randomly sample 100 people, and I just happen to end up with the number of males is 60, and the number of females in my sample is 40, right? Well, if the population is a 50-50 split, and I'm wanting to know the average income, what's going to be true about the average income I see from my sample? If it's skewed towards males, and I know that there's a gender pay gap, my sample's average income will be what relative to the population? That's how someone say, right? A little bit higher, right? I over-selected a group that I know has a higher value for that Y variable. And when I say over-selected, I didn't do it on purpose, right? It's just like if I flip a coin, you know, any 100 random coin flips, it could come up 60 or heads. Here, it just happened to be, I got 60 males. So how can I prevent this from happening? Right? Well, what if instead I broke this up into 2 groups, male, female? I will call those kind of our stratum, right? Or it's easier, we're just separating the groups, right? From each one of those stratum or each one of those groups, we'll then take a random sample that matches the demographics of our population. So I'll randomly sample 50 males and I'll randomly sample 50 females. That way I can guarantee I have an equal representation of the genders in my sample, but still selecting random people, right? Now it's not completely random because for these people, I had to make sure, you know, I wanted to make sure that I was getting 50 females and 50 males, but within those categories, it's still random. Right? I could end up with someone in Connecticut, somebody in Delaware, wherever. So once I take those random samples from each of my strata, I then put them together to get my full sample. Now I can guarantee that my sample of 100 people matches up with the gender demographics of the population. Okay? So generally we want to do this if I know that there's some characteristic that influences the variable I'm interested in. So here, that's why I chose kind of gender and then income, because I know that there's kind of a difference in those two groups. We'll see this often done with things like age or maybe income brackets. Sometimes if I want to make sure that my demographics of my sample match up with the population, maybe I break it down by race or ethnicity, right? Where I, maybe I want to make sure that my sample, kind of percent of individuals who are white in that sample matches up to the population, right? And so I, maybe take, I think it's just a little bit below 50 now, I can't remember the exact numbers, but maybe I'll do 50 white individuals, Hispanic, maybe I'll do 20, and then kind of go through every single ethnicity group, and then I throw them all together, right? But I'm kind of guaranteeing that I'm getting a racial demographic breakdown of my sample that matches up with what the population looks like. Any questions on that? Not too bad to think about, I don't think. Another one that's really very similar. I mean, it's kind of just a difference in one really small minor bit difference is cluster random sampling. So cluster random sampling is I'm not separating the data into groups, but I'm sampling from multiple subsets of the population. So clusters or groups of the population that look like the population as a whole, they're just smaller. So this might be something like, I randomly sample 50 people from Chicago, 50 people from Houston, 50 people from LA, right? I've got kind of these cities that are mini subgroups of the population as a whole. Okay. Generally, this is used in terms of geography. Right? That's why I kind of use the city example. But right, each can kind of think about this as what if I wanted to have a sample, right? A random sample of 100 people. What do I want to make sure I've got way more people from California than I do from Delaware, right? So maybe I randomly sample, I don't know, 40 people from California, but from Delaware, maybe I only get 2. And then I go through all the states, kind of trying to get a number of individuals that matches up with, the percent of the population that state has overall. Now I can kind of guarantee my sample matches up with, or kind of equally represents each one of these geographical areas. Yeah.
I was just gonna ask, obviously California has a larger population.
Mhm.
So is that why you got more than?
Yeah, so the idea there would be, the male female one's easy because it's a 50-50 split, right? When it comes to state populations, I'm going to try to choose numbers that, let's say I was kind of operating like, let's say I wanted a sample size of 100. I don't think this is, it's not as high as 40. I probably should do, I don't know, or whatever, 20, right? Maybe California has 20% of the population of the US. So I want to make sure I get 20 people from California. In Delaware, to be truthful, I probably just need one person, right? I'm trying to match up with the population or percent of the population that they are. But yeah, right? I would kind of try to get these numbers to match up with whatever percent of the total population I know those states have. So I'll randomly sample from each state or from each cluster. I'll then throw them all together. Same kind of idea as we were doing with stratified random sampling. And now I've just got a sample I can guarantee kind of matches up with the population breakdown of the US. Excuse me. Kind of think. Like I said, usually this is done in respect to geography. I had someone kind of ask me once, I think a really good way to think about this is, it's just like the House of Representatives, right? It's just their sample size is what, 400 or I don't know, shows my political knowledge, right? But 4 and 5 or whatever, how many representatives there are, they kind of do a similar process with it, right? Now they're not randomly selecting the politicians, but that would be kind of the idea, right? We would randomly sample however many representatives are in California, however many representatives are in Delaware, so on and so forth, and throw them all together. So kind of the real good application for doing this is really political polls. We'll start looking at some political polls. That everyone tries to predict elections. There's always kind of you'll see, oh, this person is leading the polls by 5% plus or minus this amount. We'll eventually get to figuring out how they're coming up with those numbers. But from their sample, what they should be doing is using this cluster sampling, so they're making sure that they're not having one area over or underrepresented. You could even get real tricky and do cluster random sampling. And then maybe within California, you've got 10 males and 10 females, right? So you kind of do this combination of cluster and stratified random sampling. You're just doing like multiple stages. I'm not gonna like have you guys do anything like that, but I'm just kind of mentioning what it could look like. This isn't really a data collection class. If it was, we'd go kind of deeper into these issues. So here's kind of the summary, right? Is if we came to population data, we got some tools and tricks. We want to make sure we're getting a sample that matches up with our population, or that's not going to be biased in any direction. Okay. So what could go wrong, right? So we've kind of got this old historical example that kind of allows us to go through this pretty nicely, which is the 1936 presidential election. Alf Landon, which great name, lost to FDR. Like we know this, right? So my grandma used to get these things. They're literally digests with these little magazines. I don't even know. I think it was like mostly just ads. But in 1936, they kind of were pretty well-known household magazine, and they got this idea that hey, our next volume, or whatever their next magazine they put out, let's try to predict the election, right? And see if we can predict it before it happens. If we get it right, maybe that builds some reputation, and then people kind of are more likely to buy or kind of subscribe. So they sent out 10 million survey cards, right? And they got 2.5 million back. So I don't know what other courses you've taken or if you've talked about kind of data collection or survey. This is a great response rate. To get 25% of people to respond to a survey is great. That's why I get emailed all the time to fill out some survey for a chance to win a gift card, right? I never do it. All right. So the fact that they're getting 25% was awesome. They have 2.5 million people. That should be more than enough to predict the election, right? So they predicted a landslide, right? 57% of the popular vote, 370 to 161 electoral votes. Now, what the problem was they actually predicted this landslide for Alf Landon. Well, we know that's not the case. And although maybe Trump would, I don't know, argue he had more, I mean, this is like all the electoral votes, right? This is I'm not a history buff, but I have to imagine, other than maybe the first few presidential elections, Roosevelt won like all the electoral votes. And it's got to be one of the highest ones. So how did they get it so wrong? Predicting it for the other person as a landslide, and the actual outcome was a landslide for the opposing candidate. So we'll kind of use this and walk through it and figure out what in their process went wrong. So being stupid here, but right. They make math errors. They use the wrong kind of population sample variance formula. Well, that wasn't the case. But what if, of these 10 million survey cards, they sent more of them to Republicans? Well, then when they get the responses back, it's going to be more likely to look like the Republican candidate's going to win. So was there something in their process where they were over-selecting Republican individuals? Right? Maybe Republicans were just more likely to respond. So even if I sent 5 million surveys to Republicans, 5 million to registered Democrats, and I got 0 Democrats to respond, but 2.5 million Republicans, well, that's going to skew my data as well. So these two ideas we're going to kind of talk about more specifically are going to be our selection and our non-response bias. Are we over-selecting a certain group, or is one group more likely not to respond? Right? So we've got our selection and our non-response bias. Okay. So we'll use this election to think about these. I'll kind of give you some other examples, and I think we might even talk about the 2016 election at the end of the time. So selection bias, we need to make sure we have a sample that reflects the population, and we're not over-selecting Republicans in this example. Right? Now, the problem was what the Literary Digest did was the names they had, the 10 million people they sent these surveys to, they got the names and addresses by cross-referencing telephone books and car registrations. So in order for them to kind of have your name, you had to own a car and you had to have your own telephone line. Okay. Problem is, this is 1936. So who's having their own telephone line and automobile in 1936?
Rich people.
Really rich people, right? And it tends to be, not everyone, but when we're talking about averages, wealthier individuals tend to vote more Republican. I'm not the biggest political buff, but I imagine it's something to do about keeping your money, right? So we've got this process where we collected the names, but we're over-selecting wealthy individuals, which are inherently going to be more likely to vote Republican, which is gonna bias our results to thinking the Republican candidate's gonna win, right? So this is our selection bias. And this paper that came out, I don't remember how many years ago now, 20, 25 years ago. They found a bunch of people who were alive in 1936. They sent them a survey card, they sent them a survey card, see if they responded to that, and then went and interviewed the individuals to see who did you actually vote for in the 1936 election, right? And what was your car telephone ownership at the time, right? So they can kind of retroactively go back and look at what kind of the breakdown was between the groups. So what they found was of people who owned a car and telephone, 53% of those people actually did vote for Landon. So this is pretty close to what the poll got, 57%, so a little bit off, but that was because they were only selecting people who had a car and telephone. Well, they made up only what, 27% of the population at the time. If we looked at people that only owned a car or only owned a telephone, it gets kind of interesting. These are still going to be somewhat wealthy individuals, but if I only own a car, I don't have my own telephone, I'm probably more likely to be rural, right? If I only have my own telephone line, but I don't have a car, I'm more likely to be kind of in an urban area. And so what we found from these two groups, or what they found from these two groups, is that in these groups, 60% of the people ended up voting for Roosevelt. The problem was none of these people got a survey card. So if this poll had, instead of cross-referencing, just sent them to anybody who had only a car or anybody who only had a telephone, it's likely they would have gotten the prediction correct, right? But they didn't. They cross-referenced the names. They only ended up with people that had both. And then if you kind of look at people who had neither, you kind of think, well, these are probably very poor individuals, or not very poor, but they're on the low end of the distribution at the time, and they were much more likely to vote for that Democratic candidate. Okay. Any questions on this idea? So we can shut down the selection bias a lot of times, or we can at least think about how can we do these surveys in a way that we don't build it into our sample. The non-response bias is a little bit tough, right? So when we're looking at this non-response bias, I mentioned that before they interview these people, they also sent them some type of political survey. So this was like in what, I don't know, 2000 or something. And they saw, did these people respond to this survey that they gave in 2020, not the original one? And what they found was, of the people in this car and telephone kind of category, the people who actually ended up voting for Landon and the people who actually ended up voting for Roosevelt, the people who voted for Landon were much more likely to respond to this survey, even what, 60 years down the road. Now, what's interesting here is it doesn't matter which group we look at, only a car, only a telephone, or neither, for whatever reason, people who actually voted for Landon were always more likely to respond to these surveys, right? So there's actually a paper written about this, and they go into some discussion about people that are a little bit more right-leaning tend to be a little bit more involved in politics, and so it's always going to be a little more likely you get a response from political surveys from that group, and so you kind of want to make sure you factor that in, because you can't control who responds to you, right? But if you know that Republicans have a little bit higher of a response rate than Democrats, maybe you want to make sure you send a few more of those mailers to Democrats so you can kind of get an equal representation. So this one, was also built in to make it look like the Republican candidate was more likely to win, but it wasn't anything that necessarily the poll could have changed, right? They didn't know this going into it, that Republicans were just going to be more likely to respond to their survey. So we had this non-response and the selection bias built in. What are some other things that can go wrong? And I've got two examples we can think about all these biases. So people might lie to you, right? Either maliciously or non-maliciously. So the non-malicious one is, think about if I'm asking someone about what how many times in the past year have you, I don't know, visited a gym? Well, they probably don't have it recorded in front of them. They're going to do it from memory. They'll tell me a number. They'll probably round it to like, 20, right? Maybe it was actually 23. They're not trying to lie to you, but they're just doing it the best they can from memory, right? So sometimes you'll get some non-malicious lies. You'll also get people to maliciously lie to you. So if you look at like drug use data, it's amazing. It looks like nobody's using cocaine, right? If you look at survey data about drug use, but right, it's probably because people are maliciously lying to you, okay? So we've got to think about both of these going into it. We also have kind of a newer area that's being looked at is the subjectiveness of the question. So sometimes this could be as simple as it's not phrased well, and so people misunderstand it. But I saw this interesting, this was in the 2020, right before the 2020 election. Fox News had 2 polls, and they were basically, both the questions were trying to get at whether people had a favorable view of Donald Trump in presidency. But one of them, they led off the question listing a bunch of things that were good, and the other one they listed off of things that were going bad. Lo and behold, the one that listed off a bunch of things that were good made it look like the favorability was much higher than the one where they phrased it and before they asked how, do you have a favorable view of the president, they listed the negative things, that favorability was much lower. So sometimes just the way you ask the question, the way you frame the question can elicit very different responses, right? Both the questions were trying to get at the same thing, but because they preceded it with either good or bad things, they kind of influence the results they were getting. So there's a lot of kind of research into this. There's things about you don't want to use certain words even because they create they relate to anger or they relate to joy. And so you can kind of skew results from that as well. Like I said, if we had a data collection class, we could spend a couple of weeks probably on this kind of point. So let's kind of think about this. And we'll use the iClickers today, kind of give you guys credit for being here. No right or wrong answer here. It just allows us to kind of think about some biases that exist in other data collection. So let's say I wanted you to rate your health today from 1 to 4, all right? I'm gonna don't think about it for too long. I get your responses in here and then we'll kind of talk about it, okay? So if you had to rate your health today from 1 to 4, choose the one that best matches you, and we'll kind of talk about it. There we go, 13 of us. All right. That was what I had counted. So, man, someone's not doing so hot today. Okay, so what could have been true about the person that responded with a 4? What bias could have been built in here? Maybe I just didn't.
You didn't sleep last night, maybe?
Well, it could be, right? Or maybe they read the question wrong. Maybe they thought 4 was actually the best, right? It's a higher number. So this is one you really got to be careful that, the question is easy to understand and that there's not going to be anyone misunderstands that, 1 is higher or, 1 is better than 4, vice versa. What bias did I kind of shut down by making this an iClicker question? So the first 2 I said were the selection and non-response bias. If you wanted to get the point, you were going to respond, right? So by creating an incentive, kind of like the people that send you emails and tell you can win a gift card, if you create incentives, you can shut down that non-response bias or be more likely to shut it down. Now, if I didn't have this as kind of an iClicker question, what kind of people do you think are more likely not to respond to a question like this? People who are unhealthy. So what is that instantly going to do if I'm calculating a mean for health from this data? If people who are unhealthy are more likely to not respond, it's going to look like health is higher than it actually is, right? So I've got to be concerned with that non-response bias. Selection bias. What should be true? I over-selected college individuals. What should be true about your health relative to the population? I would venture to guess that all of you are healthier than an 80-year-old person right now, right? And so if my population has much older individuals, I've over-selected a young group. Age is going to be very highly correlated with health, right? So I kind of have a built-in selection bias by using you guys for that data. People might maliciously lie to me. Maybe people who don't feel like they're in good health, maybe they kind of over-exaggerated how good they feel. But here we have 2 non-malicious ways people could lie to a question like this. One, what if I felt like a 1.5 today? Well, you're kind of forcing me by the way that I wrote this question. I'd be forcing you to non-maliciously lie to me. You can't tell me that you're a 1.5. You had to choose either 1 or 2. So you're not trying to give me false data or inaccurate data, but just the nature of the responses that you had available to you kind of forced you to do that, which is why kind of open-ended questioning is usually preferred on surveys. The other non-malicious lie could be, which is interesting, is that for whatever reason, they've done this where they ask people to do self-reported health, and then they do blood pressure measures and all these other things. People, for whatever reason, always think they're more unhealthy than they are. And they always kind of underreport what their health is, right? So that's going to kind of bias our data down a little bit. So we've got all these biases that exist. I think I mentioned all of them here. I've got them in the slide, but we can start to kind of think about them. All right, so I'll ask you the second one just for the sake of having a little bit of fun. So we'll talk about some bias that exist in this in just a second. But let's say I ask you how many alcoholic drinks you have on average each week, right? So if you had to respond in one of these four categories, right, which of the four, and I won't look at this and try to, I'm not going to look at your individual names on this or anything like that. Confidential. All right, we got 13 of us in here. Kind of get going here. So, what biases might exist? Right? If I look at the data, let's just, I was a little bit scared on this one. Okay, well, we like to have fun. So, all right, what's going to be some of the biases that might exist? There we go. Well, first of all, if I have individuals who aren't 21, some people might be responding 0, right, and maliciously lying. All right, if you're worried about me looking at the data and giving someone else, like that could be bias that's built in. My non-response bias, once again, created some incentive to shut that down. But let's say that it didn't give points and you didn't have to respond to that question. Who's probably more likely not to respond to that?
People who drink a lot.
People who are in the higher categories, right? So I'm going to have that non-response bias built into a question. Kind of goes with like the drug use data I was talking about earlier, right? You're always going to have this inherent non-response bias built in when you ask something like that. People might maliciously be lying to you too. There's always the one guy at the party who wants to tell you how much that he can drink, right? So you might have people kind of just maliciously lying to you here. Hopefully, the other one you can easily think about is, once again, over-selected college individuals. I probably have a selection bias going on. What do you think is probably true about your drinking habits relative to the population? On average, they're a lot higher, right? I definitely don't drink like I used to in college, okay? So, right, we have these other biases built in. Here, another non-malicious lie. This is the idea of like when I'm asking somebody about how many times they did something in the last year. Who records how much? I'm just telling you the best I can from memory. Maybe if I'm kind of on the cusp of one of these categories, I'm not really sure, I don't know, it's 5 or 6, but I've got to answer one of them, so I choose one, right? So people might non-maliciously be lying to you as well, just because they don't keep track of it. Right? So, kind of just some fun ways to think about these different biases. We got one more example. Get out here a little bit early today. So I think this is pretty interesting. I will try to get the article up on Canvas. I tried to find it this morning, and I don't know where I put it. But I remember reading the article, so I can at least talk about it. So in the 2016 election, every polling company basically predicted the election wrong. Like there was one, I think Reuters was the only one that had it correct, right? So why did almost all of them, and I put last election, it was the 2016 election, why did almost all of them get it wrong, right? So this paper went through and did some exit surveys on polling stations and tried to get at why were these polling institutions getting this incorrect? Was there a selection bias? They didn't really find evidence of that. Maybe we have a little bit of selection because a lot of these companies are centered in large urban areas. Larger cities, urban areas tend to be voting a little bit more Democratic or lean to the left. So if I'm relying on the physical location, right, of being in these large cities, maybe inherently these polls are going to be built in to have a little bit of a left-leaning bias, right, towards the Democratic candidate. Now, the paper says this probably really wasn't playing a role. A lot of these companies have been around for a while. They're smart. They know this. And so they try to randomly sample across the entire U.S. Right? But what they said another selection bias can be is that individuals who end up on call lists, individuals who end up on polling lists, tend to be people who are more politically involved, right? And less educated people tend to be a little bit less likely to be involved. Lower education levels at the very extreme end, we tend to see kind of be a little bit more towards the right? So there might be some selection bias going on. Non-response bias, this was probably a large part of why they were getting things wrong. Okay? So if I'm asking someone what candidate they're going to vote for in the upcoming 2016 election, at the time, who do you think was more likely not to respond? People who were planning to vote for Trump. Right? Why? I had another class, we were talking about this, and the idea was, well, there's a social cost, right? It wasn't like the most socially acceptable thing to kind of have that as an answer, right? So we kind of have this non-response bias built in, right? That these Trump voters are just kind of staying quiet, right? They're getting these surveys or they're getting a phone call, they're just not responding, right? Or they kind of had unintended lying, right? Where maybe they weren't sure who they were going to vote for. And so maybe at the time they said, I'm going to vote for Clinton, right? Because there was a little bit of a social stigma, even if they were undecided, right? So they might be more likely to kind of respond with a Democratic candidate. And then what they also kind of have was this malicious lying, which they paper called these shy Trumpers, or people who knew they were going to vote for Trump, but because of that social cost or that social stigma, they were not telling the polling places they were going to vote for Trump, right? They were maliciously lying, kind of once again biasing in the direction of the Democratic candidate. So what this paper did is pretty interesting to kind of point this out and just kind of about surveys in general. So a lot of these polling things were doing phone calls, right? But some of them were starting to use online platforms as well. And when they looked at the kind of predictions from their phone kind of surveys relative to the online platform surveys that were just, there was no human interaction, they found that the online ones were much better predictors. That these shy Trumpers and kind of these non-response people, you didn't have that built into the online platform because there wasn't really a social cost. There was nobody on the other end that you had to tell that you were voting for Trump, right? And so they kind of use this to maybe make some policy suggestions in the future, which is, these polling companies should stop relying on door-to-door surveys, phone call surveys, remove the human component, because if there's any social cost to voting for either candidate, right? And this could happen in an election down the road, and the Democratic candidate is the one that people don't want to admit that they're going to vote for, right? That we should try to keep these pollings kind of online, these online platforms, completely remove the human element so people don't feel like there's a social cost or they're not worried about the social implications of whatever their response is in terms of what candidate you're going to vote for. Yeah. So I'll try to find that, put that up on Canvas, and if anyone's interested more, they can kind of read more in depth into that article. But this is some of the things that we talked about today, kind of applying to pretty recent event. Okay. So we'll pick up on sampling distributions next week. I'll put that Excel assignment. I would suggest kind of starting on that first third of it, get that out of the way, since it's stuff that we covered this week. Okay. All right. If there's no questions for me, have a fun, safe weekend. I will see you guys on Monday.